Hello, I'm Mr. McBrien. This is TEJ3M, Hexadecimal Number System. The Ontario curriculum states that students will demonstrate an understanding of the use of binary numbers, hexadecimal numbers, and Boolean logic. Today we'll focus on the hexadecimal number system. Of course, we don't have 16 fingers. 16 isn't a natural counting base for us. However, the number 16 does pop up a lot in human society, in part because of its unique properties. So, of course, it's an exact square, 2 to the 4 or 4 to the 2. We can add the first 4 odd numbers to get 16. A compass point divided into 16 points, etc. Now, we saw last time that computers can only store and manipulate data in a binary base today, base 2. And it might seem strange to us with modern compilers and such, but the earliest computer programs were actually written in binary. And so they were written exclusively in zeros and ones. And this made programming and debugging extremely challenging because humans are prone to errors when the human eye looks at large groups of similar looking objects, as illustrated here off a coral reef. And so we needed an effective method to display large binary numbers, something that we could read and manipulate more easily. And the problem is that base 2 doesn't convert to base 10 very easily, as we saw last time. On the other hand, it's very easy to convert large numbers to and from hexadecimal. You can find converters online, of course, and we alluded to those last time for binary. There are also ones for hexadecimal and octal. So you can have a look at those. But for this class, you need to be able to do these conversions without these specialized tools. As we saw last time, each unit in these numbers corresponds to a power of its base. So for binary, it was 2 to the n. For decimal, it's 10 to the n. And for hexadecimal, it's 16 to the n. So our 1s are 16 to the 0, our 16s are 16 to the 1, and so on. Now, since we only have 10 digits, we only created 10 numbers when we started building up our decimal system. So instead we use letters to represent the additional 6 digits that we need. So our 10s are in fact A's, our 11s are B's, 12s are C's, etc. And this can look a little strange at first, but you've already seen probably a few instances where numbers are represented in hexadecimal format. So we can see it in programming, and we can see it in dialog boxes inside Windows, and we can see it especially in application areas. We can see these numbers pop up. Now the good news is the conversion between binary and hexadecimal is really quite simple. The reason for this is that each group of 4 binary numbers can be converted into a 16. And so what we can do is divide up our binary number into sets of 4 and then do individual conversions into hexadecimal numbers. This is much simpler than if we do conversion, for example, to decimal. And we can call those nibbles, and each nibble can have a value between 0 and 15. Or if we want to be a little bit perhaps more accurate, a value between 0 and f. So we can replace each nibble with the equivalent hexadecimal digit. So the one furthest to the right being an A, then a 3, then an E, then a 9. And so the conversion of this 16-digit binary number is the 4-digit hexadecimal number 9E3A. And we can work the opposite way as well. We can take each hexadecimal digit and convert it into 4 binary digits, working from the right. So this extremely large multiplication, division, subtraction problem, addition problem of converting E7F4C01D can be broken into 8 small conversion problems. D converts to 1011, 1 converts to 0001, 0 converts to, go figure, 0, and so on. So we've converted an 8-digit hexadecimal number into a 32-digit binary one. Sometimes you're going to convert from decimal to hexadecimal. We can use the long division process that we used doing binary. So we can make up a table like we did previously, works very well, and start by comparing the numbers, creating a remainder, and moving onward. But you can see that this is a much more complicated process than converting to and from binary. And from hexadecimal, we use the columns method. Again, reasonably simple, but a better task for computers, to be honest, than for human beings. You will be responsible for these conversions to binary for the final exam. The good news is you'll have a calculator available to you. So we can see here that our 5, we multiply it times 16 to the 3. Our F, we multiply it times 16 to the 2. 7, we multiply it times 16. And B, we multiply it times 1. And so our number, 5F7B, becomes 20,480 plus 3,840 plus 112 plus 11, or 24,443. You could always, if you really wanted to, convert from hexadecimal to binary to decimal. I'm not certain that's a great deal more practical. Do keep in mind that you a lowercase h, this should be a lowercase h here. This lowercase h denotes hexadecimal base. Also, it's useful to keep in mind that even though computers display these hexadecimal numbers for us, they don't store this way. Everything is stored in binary. This is really just to make it easier for computers to interact with human beings. Okay, so you can try some interesting examples. Converting face, for example, to binary. You should get, I'm not going to read out all the ones and zeros for you. Converting this to hexadecimal. So, to summarize, computers manipulate and store values in binary, but they usually display them for human beings in hexadecimal format. They're convenient because each group of 4 bits in binary corresponds to 1 hexadecimal digit. Hexadecimal digits, we have to add the extra A to F digits to represent the 6 digits that we don't have in the decimal system. Of course, each digit represents a power of 16, and we should keep in mind that we can have a lowercase h after the after the numbers, or a subscript 16 to denote hexadecimal. Remember, just like binary, it can't always be clear. It won't always be clear from the number whether you're looking at a hexadecimal output or a decimal one. And so we use those to denote them. For your homework, please do the worksheet that is on Google Classroom, and I've even included some addition problems for you to consider for fun. Thank you. Have a great night.